This video is about the electric field intensity, or the electric field due to a surface charge distribution. So we will apply the electric field intensity equation based on the Coulomb's law to find out. Suppose this is how I am showing you my charge distribution. So this is a surface charge distribution with the surface charge density. So rho s is my surface charge density, which is equal to the charge per meter square, and I want to find the equation of the electric field intensity, which is given by kq divided by r square into the unit vector. So this is my equation which I have to apply. So if I am considering an infinitely small charge dq, which is located here, so this is where my dq charge is located, and I can say that my dq is equal to rho s into ds, that is equal to charge per meter square into meter square. So this will give my charge. So that is my dq. So this is the first equation which I am using, and this is the second equation which I am using. And again, if I am substituting this in the first equation, so my electric field intensity will be integration of k, or will be the line integration of along the k q will be q rho s ds into r divided by r squared. So how to find my position vector r. So this is my third equation which I'm getting. So to find my r, which is a vector, so the r in this case is equal to the vector r. So to find out my vector r is equal to a summation of these two vectors. So the first vector is OP vector and the second vector is the OQ vector. So this is the first vector and this is the second. So these two vectors are summing up to form my r. So if I'm writing my r will be equal to rho a rho. So this is my rho if I'm considering the cylindrical coordinates, and so the summation will be in this direction. So this vector will be not my OQ vector, but it will be my QO vector, since I am adding these two vectors in this way. This is my Q and this is my O and this is my OP vector. So this is how I am doing my summation. So what you need to take care of here is that this is again my r vector. So I'm summing up with my QO vector. So what is my QO vector here? So my QO vector is rho a rho and plus summation of my OP vector, which is z a z vector. So if I'm simply considering this point as z, so my r square is equal to rho square plus z square simply, and my magnitude of the r is equal to rho square plus z square raised to 1 by 2, that is square root. So if I'm substituting the value of in this, what I will get is equal to my equation is equal to E, which is a integration of, or this equation, it will be, I can take my k out and it will be rho s ds into rho a rho plus z a z divided by rho square plus z square raised to 3 by 2, because this is a unit vector again, as it will be like r by r, and you're having a r square in the bottom, so this will be give 3 by 2, and this will be the minus because we are considering this OQO, so there will be a minus sign here. And your ds can be written as, so if this is my angle phi, so your area will be made up of two components. One is d phi and one is d phi, which will be rho d phi, uh, d phi and rho dq. So, or again it's like this area will be made up of two. One is rho d phi and the other is the rho d rho itself. So my ds will be d rho into rho d phi, which will be equal to rho d rho into d phi. So again you will have to substitute that here, so your equation will become k is equal to rho d rho into d phi into d. So it was like the surface charge density, which you'll have to take it as it is, that is rho s, and you have for ds this you have substituted here, and then as it is you are taking it. So this is the next step, is that the component in whatever you are having is in the z direction, so you are not having anything in the rho direction, because if there is a field due to the rho direction in this direction, there will be always an opposite field in this direction, so it will cancel out. So this total part will cancel out in this case, and your final equation will be only in the form of z. And if you are having the rho, if you are taking the rho as outside, and if you are taking the value of the k as 4 pi epsilon naught, and if you are taking the value, if you are integrating the phi from 0 to 2 pi, which will be the phi will be varying from 0 to 2 pi, and your z will be varying from minus infinity to infinity, then your values will become z az into rho d phi divided by rho square plus z square raised to 3 by 2. So you'll have to integrate this, so there's a long process to integrate this, and I will just quickly go through the steps. So I will erase all this. So this you'll have to keep this in mind. So next step is the integration part. So whenever you are integrating the phi, you will integrate it and you will find what is the rho s into 2 pi z divided by 4 pi epsilon naught into 0 to infinity rho square plus z square raised to 3 by 2 d rho and the vector in the direction of az. So when you are integrating this and solving, you will find rho s 2 pi into z divided by 4 pi epsilon naught into 1 upon z and az. So this is, so this z and this z will cancel, so and this 2 pi and this will cancel, and there will be only 2 here. So your equation will be finally will be equal to rho is equal rho z upon 2 epsilon naught and az. So your field will be the electric field intensity, whichever you are getting, will be in the direction of the point, which is in the direction of the z which we had taken. So this is the final equation of the electric field intensity due to a surface charge distribution you are getting. So this can be your raise z, because the plane you are considered was the xy plane and the point was located in the z plane. So again this will vary accordingly, and you can write it as E for the field in n direction or in the n direction as rho z upon 2 epsilon naught into an. So this can be the general equation. So that's all about deriving the equation for a field due to a surface charge distribution. Similarly, you can derive for the volume charge distribution also. So I will not cover the volume charge distribution in this lecture. So if I'm getting requests in comments, or if I'm getting requests to do that, I will do. But if you have understood how to derive it based on the point charge or based on the surface charge, then you can easily also derive it for the volume charge distribution. Also you can take help of the other reference materials available to you to do that. But if you are requesting me in the comments in any time in future to do that, and if I have time, then I will make a derivation video for that.